Hello, this is Mrs. Ward, and I am going to go over the Chapter 3 review worksheet. So the first ones are designed to be is something that you should be able to do without a calculator because, well, the graph is graphed for you already. The first one is find the limit of -1 as x. Find the limit as x approaches -1 from the left. So from the left, I'm approaching -1, and if you want to put in that line to remind you where you're going here to -1. You're approaching from the left, so you're coming in this direction here, and that limit looks like it's going to be 2. When I find the limit as x approaches -1 from the right, I'm coming from this direction, and that limit appears to be 6. Since these two are not the same number, then the limit of -1 without a direction does not exist. And then it says identify any intervals which the function is continuous. It's continuous everywhere except for 2. So you can say -infinity to +infinity, x cannot equal 2. Or you can say -infinity to 2, union to +infinity. Either one of those answers is correct. Okay, moving on to the next one. Evaluate the following. So now I'm still approaching x is equal to -1. So I'm going to draw a line at -1. And as I approach the limit as x approaches -1 from both the left and the right appears to be 1. Then once the limit as x approaches 1 from the right, well, this is coming from this direction from the right, which is this guy, that's still going to be 1. As I approach, oh, the first one was from 1 to the left, 1, and then this will be 1, and then f of 1 is also going to be 1. So the reason why the limit exists, both sides exist, f of 1 exists, is because it's continuous at 1. In fact, looking at this function is continuous over the interval of -infinity to +infinity. The next one, it says if the limit of f of x is equal to 2 and the limit of g of x is equal to 3, then find the limit as x approaches c of f of x squared. So this will be 2 squared minus 2. G of x is 3 times 3 plus g of x squared, so 3 squared. And so this will be 4 minus 18 plus 9. And when I do all that, I get -5. For each of the following limits, find each of the following limits analytically. If the limit does not exist, choose the best answer from the following choices: -infinity, +infinity, or does not exist. So when I have the limit as x approaches 2, I can do direct substitution here because that is a continuous function. And when I do all that, I get 17. So that is my limit. Doing the next one, it's a piecewise function, so I'm going to put 2 in when x is less than or equal to 2. So this is approaching from the left. This is approaching from the right. And when I have 2 minus 1, I get 1. And when I have 2 times 2 minus 5, I also get 1. And since they are the same, actually, they're not the same. This is -1. Whoopsie. Not the same. Not the same. And since they are not the same, the limit does not exist. The next one, find the limit as x approaches 1. So I'm going to have 1 squared plus 4 is equal to 5. So this one, when x is equal to 1, this is 2, but this only happens when x is equal to 1. So I can imagine this graph poorly drawn. And when I have 1, I can imagine this graph. I have this one place where it's not equal to, because for some reason it's equal to 2. So this is what this graph looks like. It is a hole. So the limit does exist, and that limit is going to be 5. The next one, limit as x approaches -1. Well, if I try and put -1 in, I get 0 over 0. So that's that indeterminate. It means I don't know really what's going on. So I am going to factor the numerator. The numerator factors is x plus 1, x minus 6, all over x plus 1. I'm still taking the limit. as x approaches -1. Here the x plus 1 simplify. So when I take the limit as x approaches -1, I can do direct substitution at this point, and my answer is -7. Moving on, I have an absolute value. This one is a directional, so I should be able to find it. It's from as x approaches 3 from the left, So I'm going to pick a number from the left of 3, which shows, let's say I think of like 2.9. So if I do 2.9 minus 3 over 2.9 minus 3, this in the numerator would be -0.1, but I'm going to take the absolute value, so that would be 0.1 over -0.1. So this will be -1. So from the left, this limit is equal to -1. From the right, it's probably equal to +1. Limit as x approaches 0. Again, this is where I get that indeterminate. I get the 0 over 0. So that means I am going to somehow do something algebraically. Since it is a radical, I am going to multiply by the conjugate. So I have the square root of x plus 4 minus 2 over x. Multiplying by the conjugate, I'm going to have the square root of x plus 4 plus 2. And I have to multiply both the numerator and the denominator by the same thing, since I'm not changing my fraction. Now here, when I multiply, when I take the square root of x plus 4 times the square root of x plus 4, that'll just be x plus 4. Then remember, my middle term will go away, and then -2 times +2 will be -4. And this is all over x times the square root of x plus 4 plus 2. Then what's going on is the 4 and the -4 will equal 0. So that means I'd be left with just x, and then at that point I can simplify the x's, still taking the limit as x approaches 0 of 1 over the square root. In place of this x, I'm going to write 0. And when I do that, I'm going to have the square root of 4, which is 2, so I'm going to have 1 over 2 plus 2, or 1/4. And that is going to be my final answer. The next one, when I put 0 in, it becomes undefined. So what I'm going to do is I'm going to multiply by the least common multiple. The least common multiple will be 13 times x plus 13, because that's all my denominators. So I am going to take this 1 over x plus 13 minus 1 over 13, and I'm going to multiply that by 13 times x plus 13. And my x, which is in my denominator, I'm going to multiply it by the same thing. So what happens when I multiply this times this, the x plus 13s will simplify, and I'm left with 13 times 1, so that'll be 13. Then when I multiply this times this, the 13s will simplify. I'm left with this -1 times x plus 13. And this is all over x times 13 times x plus 13. I probably should have written that differently. I'm still taking the limit as x approaches 0. Then what happens, distributing my negative sign, I'm going to have 13 minus x minus 13. I'm going to write this as 13x times x plus 13. Now in the numerator, the 13 plus the -13 is equal to 0. Then the negative x and the positive x will simplify, and the whole numerator is going to be left as -1. So I'm going to have -1 over 13. And then remember, still taking the limit as x approaches 0. So in place of this x, I'm going to write 0. So I'm going to have 13 times 13, so 169. And that is my limit. The next one, when I go and I put in 2, it's undefined. It's 1 over 0. So this, in other words, I have x is equal to 2 is where it's discontinuous. It's non-removable. So it is probably going to have an asymptote. So I am going to pick up my calculator and graph it. And when I graph it, I get something that looks like this. I want to graph it right. Something that looks like this. And or if I wanted to test it, I could test it. Let's test it. If I wanted to pick like as x approach 2 from the left, I would pick like 1.9, so that would give me 1 over 1.9 minus 2 squared. Well, that would be a negative 0.1 squared. It's still going to be positive, so this would be positive over positive, which would be positive infinity. If I found the limit as x approached 2 from the right, so now I'm going to use 2.2 minus 2, or 2.1 actually, squared, and then I'm still going to have a positive divided by a positive, so I'm going to get positive infinity, which is what I got from my graph. So my final answer, remember, my limit does not exist, but my best choice is to say positive infinity. The next one, I go to put in 3. Well, this factors is x minus 3, x minus 3. It's discontinuous at 3. They're non-removable discontinuities, so I know I'm probably going to have a vertical asymptote. So I am going to, I graphed it. No, I did not graph it. I lied to you. I did not graph it. So when I do this, let's say I pick, so we can write this as x minus 3 squared. So no matter what, this 3 is always going to be positive. So let's think about this logically. When I take the limit as x approaches 3, this 3 over x minus 3 squared. It doesn't, 3 will always be positive no matter what I put in. And it doesn't matter if I put 2.9 minus 3 and I get a negative number squared, or if I put 3.1 and I square. This is always going to be positive because I'm raising it to the second power. So this whole limit is going to be positive infinity. Again, remember the limit does not exist, but the best choice is to say that it's positive infinity. The next one, as x approaches negative 3 from the left. So I tried to factor because that's what I did first. I got x minus 2, x minus 1, and then this factors is x minus 3, x minus 2. That's how that factors. Still trying to find the limit as x approaches 3 from the left. The x minus 2's will simplify, which really doesn't help me because I want to find this limit here. But I'm left with x minus 1 over x minus 3. But since I'm coming from the left, I'm going to pick like 2.9. So I'm going to have 2.9 minus 1 over 2.9 minus 3. So this will be a positive number over a negative number. So this whole thing is going to approach negative infinity. Again, if I graphed it, I would see that, and I could do it that way. Number 5, list any vertical asymptotes of the following. So vertical asymptotes, remember, are non-removable discontinuities. So I'm going to factor the numerator as x minus 2, x plus 1. The denominator will factor as x plus 3, x minus 2. The x minus 2's will simplify. So that is a removable discontinuity, so that makes a whole, which means it is not an asymptote. The other discontinuity is this x is equal to negative 3. So that's my non-removable. If it's non-removable, that makes a vertical asymptote. So my vertical asymptote is going to be x is equal to negative 3. The next one, I have x minus 2, and then the denominator factors is x minus 5, x plus 2. I think, if I factored that right. It does. Nothing simplifies. So I have non-removable discontinuities at x is equal to 5 and x is equal to negative 2. Those both form vertical asymptotes. So my equations of my vertical asymptotes are x is equal to 5, x is equal to negative 2. Moving on to the next one, find any discontinuities for the following function. Identify each discontinuity as removable or non-removable. So this, I'm going to factor on x and make it x times x minus 1, x squared minus 1, over x plus 1. This factors as x plus 1, x minus 1, all over x plus 1. So it simplifies. So since it simplifies, I have a removable discontinuity at x is equal to negative 1. The next one, if I substitute in 0, I'm going to have 0 plus 1, which is 1. And then I'm going to have 1 minus 0, which is 1. So they are equal to the same number. They are the same, which means that my limit exists, which means that there's no hole, there's no break, it's continuous. So this is not discontinuous. So it is continuous. So there are no there are no discontinuities, so nothing's removable or non-removable. This factors is x plus 3, x minus 3. Neither one simplify, so I have a discontinuity at negative 3 and a discontinuity at positive 3. So I have non-removable discontinuities at x is equal to negative 3 and x is equal to positive 3. They form vertical asymptotes, but it doesn't ask me to tell you that, so I didn't tell you that. It says determine the value c so that f of x is continuous over the entire real number. So the only place I'm going to have a problem is that when x is equal to 5. So I'm going to put 5 in for this x and say 5 minus 2. In order for it to be continuous, then these two have to equal each other. So I'm going to have 3 is equal to 5c minus 3. Add 3, so 6 is equal to 5c. C is equal to 6/5. So c has to equal 6/5 in order for this to be a continuous function. Number 8, the function 12 minus x squared has a 0 over the interval of negative 1 to 5. Use the intermediate value theorem to explain how we know this to be true. First thing I have to say is f of x is a continuous function. And you can be as specific to say is a continuous function in the interval. But it's a continuous everywhere, so it's not just in that interval. It is a continuous function. So the next thing I'm going to do is I'm going to find f of negative 1. So I'm going to take 12 minus negative 1 minus negative 1 squared. And when I do all that, I get 12. And then I'm going to find f of 5, which is going to be 12 minus 5 minus 5 squared. And when I do all that, I get negative 18. So since it's a continuous function and f of negative 1 is 12 and f of 5 is negative 18, then f of x has to have, so I'm going to say, since f of x is a continuous function, I already said that, and f of negative 1 is a positive number, and f of 5 is negative, then f of x has to equal 0 somewhere between negative 1 and positive 5. You have to cross the x-axis to go from negative to positive. If you cross the x-axis, you're equal to 0. All right, describe the two circumstances under which the limit may fail to exist. Sketch the graph of any function such that all the following are true. So the two times that the circumstances in which the limit fails to exist is when you have like a jump in the graph or when you have an asymptote. So this one is saying find the limit as x approaches 2 from the right is negative 1. So here's negative 2. I'm going to just put that in here because everything seems to be happening at 2. As I'm approaching from the right, my limit is negative 1. So as I'm approaching from the right, it's negative 1. I'm just going to put a little dot there, and it can do whatever over here. It doesn't matter. As f of x approaches negative 2 from the left, it's positive 3. So it's here. And f of 2 is equal to 0. So then I have, so this is going to be an open circle. This will be an open circle. Here's my closed circle. This is what I drew. It could be anything. I mean, it could be same thing, but you could have this going like this, and you could have this going like that. It could be that. What cannot happen is I still have to pass the vertical line test. So as I'm looking at as I'm drawing vertical lines, it should only cross the graph in one place. So this is two examples of what it could look like. Multiple answers are correct. And the last one, it says complete the table. So you're having your calculator, you're putting this into your calculator, and you're doing the 3.9, 3.99, and you're showing me all the decimals that the calculator shows you. So I'm going to have 0.0408, 0.0401, 0.04, and my calculator did stop at that 0.04, 0.04, 0.0399, and 0.0392. And so I'm going to say that the limit is going to be 0.04, and that's all you have to do for that one. All right, I hope this helps, and I will see you next time.